last speaker of the school and of this afternoon is Erik Curiel. I would like to thank Erik again for accepting our invitation and in particular for his great lectures. Please, Erik, you have the floor.
Okay. Well, I also want to thank you and all the other organizers for inviting me and for allowing me to tell everyone what I think about about all of this really important and interesting stuff. And I also want to thank the audience, y'all, the participants. Y'all have been really great. You've been asking great questions here and on Slack. You've made it a lot of fun, and I've really enjoyed myself. So thank you all very much. Before I begin, so the lecture today, I'm going to do the very last part of yesterday's lecture, the epistemological ruminations, the digestivo. So I'll actually be starting the meal today with the digestivo, but I hope that's not too offensive to the Italians. I want to make a remark, a methodological remark. Especially today, several of the speakers have been somewhat apologetic for repeating basic facts, that basic pictures, constructions, claims, facts that have come up, in previous lectures. Pictures of Hawking radiation, the statements of the GSL, stuff about analog gravity. And I think it's actually important. I don't think that people should be apologetic for repeating these kinds of simple, basic things. Not only, again, is it's enjoyable by the framing pleasure principle. I think methodologically, especially in foundational work, it's not just worthwhile. I think it's actually necessary to frequently go back and think about the most simple, basic facts, claims, principles, arguments that ground the field you're working in. In my experience, that's when doing that and really thinking again and again and again about these simple, basic facts, that's where the best new ideas come from. That's where the possible avenues for attack on recalcitrant problems come from. So I encourage you to do it. Of course, you shouldn't have a talk that's only a repetition of basic facts, but I think it's almost always worthwhile to do, both for yourself and for the audience. Okay, so recall where we left off yesterday. I had argued that semi-classical gravity, if we treat and conceive of semi-classical gravity as an effective field theory, although it's not entirely clear how we do that. I sketched two possible ways one might try and do it. And I tried to argue that irrespective of which way one went, there were strong intimations that perhaps we shouldn't be taking problems like the information loss paradox so seriously, at least as perhaps telling us something very deep about a more fundamental theory. Although these kinds of problems may be incredibly important clues on helping us find a deeper theory, it's not clear to me that any problematic conclusions these kinds of arguments lead to, we should be worried about as necessarily cascading down to a deeper level of theory. And that's where we more or less left off. So consider what I call the problem of semi-classical coupling. What justification, if any, can there be for the form of the semi-classical Einstein field equation? Why should classical geometry couple to the expectation value of the operator, the self-adjoint operator that represents stress energy of the quantum field in semi-classical approximation? If you think about what an expectation value is, in ordinary quantum theory, expectation values standardly represent averages of possible experimental outcomes. So just very naively, that might imply or suggest that the semi-classical Einstein field equation assumes that classical geometry effectively acts as something like a continual measurement probe of the quantum field. And I think that is, in fact, something that people have considered ideas like that. I think some of Penrose's ideas about how gravitational interaction affecting wave function collapse might be conceived of along these lines. I've heard people try and invoke the Ehrenfest theorem in this context. I think it's irrelevant because we're not talking about the classical. So the Ehrenfest theorem, recall, says that under quite rather weak, not trivial, but rather weak conditions, if you take the time evolution of the expectation value of of a quantum system, that will very closely track what you'd expect the classical evolution of the corresponding system would be. But the Ehrenfest theorem is actually irrelevant here because we're not talking about the classical evolution of an expectation value, but rather how the quantum field operator evolves in a quantum way when coupled to classical geometry. And there have been some suggestions in the field by people like Daniel Sudarsky and his collaborators that dynamical collapse interpretations may be able to make sense of this to explain why the expectation value, why classical geometry couples to the expectation value. But there are some problems with those approaches as well. So I think this is an interesting question to consider. Mostly though, when people do think about it, which isn't very often, I'm sorry to say, when they do think about it, and you do press them on it, why is this the way we expect quantum fields to couple to classical gravity in this appropriate regime? The thought is that the form of the equation is justified because the same kinds of techniques that there are kind of loose heuristic arguments based in very flat-footed perturbative quantum gravity that one can use to derive an equation that looks exactly like the semi-classical Einstein field equation. And people, I think that because we have these very standard-looking arguments in perturbative quantum gravity that yield what looks like the semi-classical Einstein field equation, that's good enough. And I mean, the standard, when I say the standard technique and the same techniques that are used in, say, for instance, deriving the semi-classical treatment of phonons, and they're coupling to a classical fluid background, you do the completely standard move. You expand the equations of motion and power series of coupling constants. You invoke a saddle point approximation. You truncate to first order, and with just a few moves, you get that the lowest order relevant term is the expectation value that couples to the classical system is an expectation value of what kind of look like thermodynamical quantum observables of the system that you're looking at, in say phonons in this case. And so same argument gives you semi-classical Einstein field equation, done. I don't think though that we should be satisfied with that. In these other contexts, because of all the background knowledge we have about the solid state fluid systems, for instance, including both theoretical and empirical experimental justifications for these things, we know in those contexts, for instance, what the power series means physically as a whole, including understanding and having empirical evidence for its regime of applicability, where we expect this kind of power series to be an adequate representation of the physics. We know what the individual terms of the power series mean physically. We know what the saddle point approximation means physically, including, again, understanding and having empirical evidence for what its regime of applicability is, when it makes sense to apply to a particular physical system in a given state coupled to a certain kind of environment. We know what truncating the first order means, including again its regime, and so on, because we have so much background knowledge already deeply entrenched about solid state systems, fluid systems, and all these other systems in which we employ this kind of technique to derive a semi-classical equation. And because of all that, we have epistemic warrant for using, for example, the semi-classical phonon model, both for claiming that we understand it and for claiming that it is a good model, empirically, in a circumscribed regime. We have epistemic warrant for using it, in fact, even more. We have epistemic warrant for using it as the basis for further knowledge claims that ipso facto already will have some confirmatory support in virtue of being derived from this well-entrenched, well-understood semi-classical phonon model. And before I go on, to be fair, I must note that there may be some empirical support for QFT-CST, and that's particle production in early state cosmology and its possible signature in the anisotropies of the cosmic microwave background radiation. So people have wanted to, so there are anisotropies. The cosmic microwave background radiation is not perfectly homogeneous and isotropic. There are anisotropies at the level of about one part in 10,000. And people have wanted to explain these anisotropies, in fact, by invoking the analog of Hawking radiation in cosmological expansion, get exactly the same kind of particle production in this in that kind of dynamical QFT CST calculations suggest you get the exact same kind of particle production in these dynamical situations, expanding cosmological model. And so people have pointed to this and said, look, no, we really have some empirical support for QFT CST. But one has to be, I think, very careful here. The anisotropies that we're talking about that are themselves, there's no doubt they're there. That they are definitely detected. That it's as, you know, we can have as much confidence in that as we can have confidence in any astronomical observation. That's not the issue about whether or not that actually provides empirical support for QFT CST. The issue is that the derivation of the anisotropies in the framework is really not very convincing. I think when you look carefully at the details, they're basically building in the anisotropies at the right scales from the start. By the way, they set the problem up. I don't think it's a very convincing derivation at all. And I'm not alone. A lot of people agree with me on that. And in any event, even if it were, it doesn't use the semi-classical Einstein field equation. So even if it did in fact turn out to be confirmatory for quantum field theory and curved space-time, where there's no coupling between quantum field and semi-classical and classical geometry, that wouldn't be confirmatory of semi-classical gravity, because it wouldn't show us, one, that the semi-classical Einstein field equation has the correct form, and also it wouldn't show us that even if it did work for cosmological particle production, that wouldn't give us any confirmation that it works for black holes. So the issue, though, is we want to use the semi-classical Einstein field equation. We want to use semi-classical gravity as the basis for arguments whose conclusions we want to have confidence in. That's what, you know, people say. This is our best guide, you know, for clues to quantum gravity. That's what that means. I take it is we want to make arguments based on it. We want to have confidence in the conclusions of those arguments. We want, therefore, essentially to use it as part of an evidential network to buttress the assertability of claims in black hole thermodynamics, among other things. But to repeat emphatically what I already said a few minutes ago, we have none of the entrenched background knowledge about semi-classical gravity that we have about all the other fields of physics where we engage in the same formal kind of maneuvers. And so I really don't think semi-classical gravity can confer confirmation on any claims in, for instance, black hole thermodynamics, because one of the essential elements of confirmation is that anything that gets it can then be used as evidence for other claims. So that is exactly what Hawking radiation, black hole thermodynamics, and semi-classical gravity, and the whole ball of wax can't do, at least not in our current epistemic state. So I think we must be careful in trying to use semi-classical gravity to draw fundamental lessons. And there is an active danger, I think, in assuming that the semi-classical regime is now well understood and that its results may be used as the touchstone for testing programs of quantum gravity. That recovering those results acts, in fact, as a minimal criterion of adequacy, if not, in fact, something epistemically stronger. If it turns out not to have been right, and that's a live possibility, then essentially, well, all of quantum gravity has been wasted effort, maybe a little too strong, but a lot of it would have been wasted effort. I think it makes sense to hedge our bets. And again, I'm not saying that we shouldn't be using semi-classical gravity and black hole thermodynamics as the grounds for speculative investigation. Of course, we should be doing that. I'm rather saying that we should be more critical, more skeptical, and more modest in our understanding of the epistemic warrant we have for it, both with regard to our understanding of it and with regard to our confidence in using it as the ground for further investigation. We should be clearer on what our epistemic state actually is with regard to it. So some of you may have recognized that the name for this last section of the talk is an homage, maybe too strong of a word, but a nod to Kierkegaard, one of my favorite philosophers. So I thought it was appropriate to end on a Kierkegaardian theme. Shall we be a knight of faith, or shall we be a lost soul? Is there a consistent picture of space-time geometry, matter, and their interaction in this framework? Can such a problematic framework give good results, and if so, how? Why have faith in results from a framework with such manifest, serious, unresolved problems? How to make progress in important parts of theoretical physics if one doesn't have faith? So shall we make the leap of the absurd or remain a skeptic and be damned? Well, unlike Kierkegaard, I'm actually going to advocate what Kierkegaard liked in his very earliest work. I recommend Socratic irony, a dialectical process of moving from skepticism to faith and back again, as our epistemic circumstances evolve and our constant questioning, knowing that we do not know. That's the end of the epistemological sermon, I guess it ended up really being. So I will now completely switch gears and start, let me stop there and see, does anyone have any questions, comments, remarks, jokes, quips, quibbles about the epistemological sermon?
Okay. Questions?
Okay, then I guess I can only conclude that what I said was absolutely perspicuous, completely unambiguous, and so correct that one could not possibly question or controvert it, since no one has anything to say.
Yeah.
Cool. Oh, wrong one. There we go. Why are you doing this? There. Okay, good. Now can you see that? Singularities in classical and semi-classical gravity. Theory failure or groovy new physics? Well, let's find out. I'll begin by talking about a little bit about singularities in classical general relativity and cosmic censorship and determinism in that context, since the issues, I'm hoping, a little more familiar to everyone than what happens in semi-classical gravity. I'll spend a little bit of time talking about then how these issues are somewhat modified and made more complex, and I think actually more interesting when one moves into the context of semi-classical gravity. And then I will consider the question, which I know if you ask almost any physicist, they won't even think it's a question, but I think it is a question. Do singularities necessarily indicate the breakdown of a theory? In this case, general relativity or semi-classical gravity. Every physicist and her mother will say, yes, of course it does. I don't think we should answer it so fast. I think there are at least, if not absolutely compelling reasons, it's still interesting and viable reasons that are worth thinking about that might make one doubt that a singularity in a physical theory always indicates a breakdown of that theory. Okay, so recall that sometimes in relativistic spacetimes, world lines just end after a finite period of time. You can't extend them into spacetime. You can't extend spacetime itself. There's no event at which the world lines terminate. And so in some sense or other, it seems as though there's some kind of breakdown of the spacetime geometry. Something is going wrong. One way to make that very vivid, especially for with regard to our psychological, the attempt to imagine what the psychological experience of an observer whose world line that is, that observer would experience only a finite length of time of existence, but without ever dying or ceasing to exist in any way. And I think that is difficult for us to conceive. It's difficult for me to conceive anyway. So here's just a kind of rough picture. There's this tear or hole in space-time. We're going to be somewhat imprecise about it for the moment. Here's this observer just cruising along, and with no warning whatsoever, her world line just stops. She never experiences it stopping because there's no final moment. There's no point of space-time at which the world line ends. It's like if you think of the positive half of the real line and remove zero. So it's a half open ray. As you approach zero, let's say you start at 1 and you start moving towards 0. Well, you can't move more than a distance of 1 because there's nothing left. But you'll never stop because there's no final point. We remove 0. That's what's happening here. And correlatively, it might also happen. Something might just kind of pop out spontaneously, spontaneously kind of pop into existence with no first moment, and just start cruising along into space-time. This is allowed in general relativity. And so this idea of these incomplete inexplainable curves provides the canonical definition schema of a singularity in general relativity. The schema is, in a space-time satisfying the maximality condition, a singularity is an inextendable causal curve, incomplete with respect to some measure of length. And that places almost no substantive constraint on the nature or physical properties of space-time. Essentially, every single kind of space-time you can possibly imagine can have such curves. And I say this is a schema, not a definition, because both the ideas of maximality condition and the ideas of some measure of length need to be specified. And there are, in fact, many different ways they can be specified, many different ways people have specified them and argued in favor of them. So there really are many, many different, more concrete, precise definitions people have proposed. And people have also not proposed this as definitions, but merely as a sufficient condition. That's actually probably more usually how this kind of proposition is used, not as a definition, but as a sufficient condition. But we don't need to worry about those subtleties for the moment. So here are some examples of spacetimes in which there are such incomplete inextendable curves. We can just delete from the spacetime a set that's in the shape of Ingrid Bergman, and then all the curves that ran into, all the curves that used to run through the points that we removed, well, now they just stop because there's no more points left. So you can think that this might be a case of that. Maybe this is a Minkowski space, and we just reached in and ripped out those points, and so now there's no points for this world line to go to. The world line just ends. But a lot of people think that's cheating. That the real world, physically reasonable spacetimes don't act like that. I think that's a terrible response. I think that's actually just incredibly boneheaded. And I think it's really interesting to think about why it's a boneheaded response, but that would take us too far afield. So I'll just set that aside. And I'll defer in this case to orthodoxy and say, fine, let's not worry about those kinds of spacetimes. Well, we have there are theorems that show us that in fairly generic cases of gravitational collapse, there's going to be a divergence of the space-time curvature as measured along geodesics, kind of following the infalling matter, the condensing matter. And there's a sense in which this blow-up of space-time curvature seems to indicate that the metric in the space-time geometry itself loses definition at r equals 0, loses definition at kind of the point where stuff would actually, the star, let's say, would entirely condense into a single point and have infinite volume. The phrase loses definition at r equals 0 is in scare quotes because it's important to remember, I'll discuss the importance of this later on, but at this point in the talk, I'll simply remark that there actually is, in such spacetimes, there is no point of the spacetime manifold that corresponds to r equals 0. In say Schwarzschild and standard coordinates, the domain of the radial coordinate does not include the value r equals 0. So there are also some incomplete inextendable curves in spacetimes that have no kinds of topological surgery of this kind, and also have no pathology in curvature whatsoever. So top nut, colliding plane gravitational wave spacetimes are examples. I'll show you a picture of Meissner's 2D version of top nut in a moment. In fact, the classic singularity theorems of Penrose, Guroch, and Hawking show us that singularities are generic features of otherwise well-behaved spacetimes, and just completely generic features of otherwise well-behaved spacetimes. There seems no reasonable way to avoid them in anything like almost every physically realistic model of a system, of a kind of a cosmological or astrophysical system we have in general relativity. You just almost always get singularities. So here's Meissner's 2D top-down example. It's really cool. So the null cone, so time is moving forward up here in this direction. Space is a circle, so the entire space-time is r across the circle. It's a cylinder. If you look at the way the null cones, so that this going straight up is a time like geodesic. These straight lines going up cylinder are time like geodesics. Look at the way the null cones are changing as you move forward in the time like geodesic. I'm sorry, it's not a time like geodesic, it's a null geodesic because it's tangent to the null cone. Look at the way the null cones are changing as you go up the null geodesic. They are contracting and tipping up a little bit as you move upwards until you hit this circle right here, which we've labeled t equals 0. These are negative t values, these are positive t values. This actually is a closed null geodesic. So this space-time is acausal. There's a closed causal curve. This is a null geodesic that is closed. But for our purposes, what's most interesting is if you follow this null geodesic, this guy ends up wrapping around the cylinder and asymptotically approaching this t equals 0 closed null curve. This is a null geodesic, but it never reaches it. And one can in fact show that it only has a finite affine length, finite generalized affine length. So this is an incomplete, inextendable null geodesic. There are no points removed from the spacetime manifold. It's just R1 cross S1. One can easily show that there's no curvature pathology. The curvature, every single measure of spacetime curvature is well behaved. Everything is either finite or 0. But it's just the case that there's this null geodesic that winds around and never, it just winds around for a finite period of time, but never actually comes to an end. So as I already suggested with the first picture I showed you of the little black oval with lines going into a line going into it and a line coming out of it, since general relativity is time reversal, it's a time reversal invariant theory. If a world line, an observer can just kind of pop out of existence in the middle of space-time, it can also just pop in, just flip your space-time model upside down, and that's a model of a space-time which an observer just kind of pops into existence right in the middle of space-time, seemingly violating Leibniz's principle of sufficient reason. And it's actually kind of funny when you read these papers from the late 60s, when people like Penrose and Groch and Hawking and were struggling with this and trying to figure out what the hell was going on, trying to make sense of this. They would actually, in the papers they were publishing in Physical Review, they would make arguments that essentially were invoking Leibniz's principle of sufficient reason without, but I don't think they knew this. Well, I know for a fact Groch, I asked him, he had never read Leibniz. But I mean, they were just struggling to try and come up with arguments about this. And they would say things like, well, what possible, if we could extend space-time further, then what possible reason could there be to stop it before, if it could continue on further? It's actually really funny that they were speaking philosophy without even knowing it. So there doesn't seem to be any physical mechanism that could cause such a thing going forward or backward in time. This raises the problem of how to formulate the laws when space-time loses definition on this curvature pathology. But it's also the case that it's actually it turns out to be a very subtle matter to really be precise and rigorous about and unambiguous about what one means by physical significance of curvature pathology. It's often very ambiguous. Often whether or not measures of curvature misbehave, diverge, say, or oscillate without ever coming to a limiting value along an incomplete inextendable curve depends very sensitively on the motion of the observer probing these curves. So it's not entirely clear that curvature pathology is always a well-defined invariant notion, a well-defined invariant property of the space-time itself. That's a really fascinating issue. It's also the case that space-times can be time-like complete. You can have every single time-like geodesic can be complete, but null incomplete, and have incomplete null geodesics. In fact, that's what happens here in top nut. And vice versa. You can have every single null geodesic be complete, but have time-like incomplete geodesics. That seems very difficult to understand physically. Spacetimes can also be geodesically complete. Every single geodesic is complete, but there are incomplete time-like curves of bounded total acceleration. Every freely falling observer and every photon has no problem, but stick someone in a rocket ship with enough fuel, not an infinite amount of fuel, finite amount of fuel, and they will find themselves traversing one of these incomplete and excitable curves. Then there are some philosophical problems that all these issues raise. So again, just as with black holes and with many other issues in this field, there is a plethora of definitions of singularities, and not just because there are different ways of making the canonical schema concrete. There are actually definitions that don't even make use of the canonical schema. So is there such a thing as a single correct definition of a singularity? A question that has recurred time and again in these lectures. Not just about singularities, but about many of the concepts and entities we deal with in this subject. If not, what is the relation among all the at least prima facie viable definitions? Are they different explications of the same concept? Well, they can't be, because we know for a fact they have different extensions. Space-time will be singular according to one, but not singular according to another, even though both definitions seem to be really, when you just conceptually, seem very, very close, but turns out they're not. At least they don't agree extensionally. There's as I already remarked, there's ambiguity that comes from different notions of length, use of determined incompleteness. There's a problem that how one defines maximality and whether a manifold as a whole is inextendable is not a property of the manifold itself. It's a property of what class of space-times you allow as possible extensions of your first space-time. So are you going to allow just every single possible Lorentzian-4 manifold? Well, there's some really crazy ones. So let's try and winnow it down to some physically reasonable class. Well, there are many different ways of defining what one means by, or trying to characterize what one means by a physically reasonable space-time. And so depending on which one you choose, the same space-time will turn out to be either maximal or not maximal. So that that's hard to get a grip on. Then there's the question of singularities themselves. Do singularities exist? Well, the singular behavior is the incompleteness of the curve. And we can invoke the old Aristotelian maxim, to exist is to exist in space and time. But the incompleteness of the curves don't exist in space and time. There's no point of space-time at which the curve ends. And there, in a sense, one can make precise the incompleteness of the curve as a feature of the affine structure of space-time is a global property of the space-time. It's not a local property of the space-time. So what sort of existence, if any, should we attribute to them? Do they herald a breakdown of determinism? I'll discuss that in a moment when we talk about cosmic censorship. Do they herald a breakdown of general relativity as physical theory? I'll discuss that at the end of the lecture. And anyway, since once again, we're dealing with a situation where with a theoretically characterized phenomenon that we have absolutely no empirical access to, what do we have to go on besides the intuitions of eminent physicists? And when you study the literature and look at how it develops, you realize that a large part of what guides the research in this field and many other fields in GR and in semi-classical gravity, when dealing with the phenomena that we don't have empirical access to, one of the single most important guiding factors in the field of research are the otherwise unsubstantiated declarations of eminent physicists. I, eminent physicist, believe this is what goes on, and then a whole cloud of more junior physicists jump on the wagon and start researching it. that makes for, one really has to wonder about the epistemology of the field in some ways. I think, why is it that physicists, once again, physicists are getting freaked out about these things? They get freaked out about loss of unitarity. They get freaked out about these incomplete and extendable curves. I think part of, again, from reading papers and talking to people and thinking about it, I can't give you a knockdown argument that this is why a lot of physicists get freaked out, but I very, very strongly suspect, based on some evidence, that that it's really psychological, that the reason why physicists are so disturbed by singularities derives a lot from a feeling of psychological discomfort that the idea of them give rise to. There's this marvelous quote from Nabokov's novel Ada. The mind of man, by nature a monist, cannot accept two nothings. He knows there has been one nothing, his biological inexistence in the infinite past, for his memory is utterly blank. And that nothingness, being as it were past, is not too hard to endure. But a second nothingness, which perhaps might not be so hard to bear either, is logically unacceptable. I mean, Nabokov here is actually talking about death, but I think that this is, I really strongly believe that one reason why physicists are so deeply disturbed by and want to get rid of singularities really has to do with this kind of psychological issue. So let's talk now about cosmic censorship and determinism, which seems to be the nexus of issues that if you ask physicists, they're not going to say, well, I'm just freaked out because I'm freaked out about singularities because they cause me psychological unease. They're going to say, no, there are these worries about determinism, and we really want cosmic censorship to save determinism. So let's look at the reasons physicists actually say that they worry about singularities and whether or not these are really principled issues and questions to worry about. So Penrose, formula, as so often in this field, Penrose got the ball rolling. Recognized the problem initially, formulated it in a really trenchant way, and got the ball rolling. So in 1969, Penrose proposed the cosmic censorship hypothesis. Even if the no-hair, this is quoting Penrose, even if the no-hair theorem or something like it is true, have we any right to suggest that the only type of collapse which can occur is one in which the space-time singularities lie hidden deep inside the protective shielding of an absolute event horizon? If not, it would be possible for information to escape from the singularity to the outside world. In short, the singularity is visible in all its nakedness to the outside world. We are thus presented with what is perhaps the most fundamental unanswered question of general relativistic collapse theory, namely, does there exist a cosmic censor who forbids the appearance of naked singularities, clothing each one in an absolute event horizon? I don't think it's an accident that Penrose used this very normatively kind of loaded language of censorship and nakedness. I think that he is being somewhat tongue-in-cheek and playful, but also making a serious point. That again, that at least at this point in the development of our understanding of GR, there didn't seem to be any physical reason that Penrose could point to say, I have strong evidence that singularities must always be hidden behind event horizons. But it would seem to be immoral of the world to behave in such an incredibly just a loose and promiscuous way to let singularities be naked. So, as Penrose, of course, immediately recognized himself, cosmic censorship visible naked singularities, because there's one in our universe, the Big Bang. We can see it. Well, more or less. So there are two possible responses to this situation. You can either refine what one means by naked singularity, so that at least some of them, like the Big Bang, aren't problematic, because we don't think the Big Bang is problematic. That's an issue I'll talk a little bit about more in a moment. Or we can provide necessary and sufficient conditions for cosmic censorship in general, independent of the idea of a naked singularity. But in either case, the impetus is because we want to ensure determinism or predictability. We want to ensure that that the character of physics as we know it, because physics as we know it, physics as we know and love and try and do it, involves making predictions based on deterministic evolutions, and that has nothing to do. And quantum mechanics is not a counterexample to that, because one, Schrodinger evolution is deterministic. Two, we still make completely deterministic predictions about probability distributions. That's good enough. Singularities seem to admit the possibility of a breakdown of determinism so severe that we won't even be able to make predictions about deterministic predictions about probability distributions. Because if you take seriously this idea that that world lines can just pop out of nowhere, that's what a singularity is. It's incomplete inextendable curves in the middle of space-time. Well, then it would seem as though the structures that break down are required for the formulation of known physical laws, and in particular for our ability to pose and solve initial value problems. So determinism and predictability, perhaps the possibility of physics as we know it, would collapse wherever these pathologies were causally visible. So to get an idea of how severe the problem may be, think about a star collapsing. It eventually falls within a Schwarzschild radius, a black hole forms, and it collapses, in the classical picture, it collapses to a singularity. Well, because again, general relativity is a time reversal invariant theory, the following is a perfectly legitimate solution to the Einstein field equation. We're all just happily going about our business It just so happens that over there, that we haven't really noticed it, there's a white hole horizon. The white hole horizon is shrinking, and all of a sudden, just out of nowhere, this gigantic ball of star explodes out of nothing and expands and just starts hanging out and glowing as a very old star that starts to get younger. There's nothing in the law, there's nothing in the Einstein field equation, nothing in any principle of general relativity that prohibits that. But that's exactly the kind of thing that Penrose is worried about and that other people are worried about. Well, so we're worried about determinism failing, but what exactly do we mean by determinism? There are in fact many forms of determinism, and they can all fail in really different ways. That would be a really interesting talk to give by itself, just going through all those ways. But that would take me too far afield. So I'll just say you should go read these really wonderful work by Ehrman and by Yulia Stabashevsky more recently on this issue. So most of the modern attempts to formulate a definite principle of cosmic censorship, because again, it's the principle that we don't have a single canonical, well-defined, precise, unambiguous statement of cosmic censorship. There are lots and lots of different proposals, none of which are equivalent to each other, each of which seems kind of reasonable on its own. It's hard to figure out. It's hard to navigate and map the conceptual relations among them all. But one very kind of very standard, strong formulation of it these days is something like the following. The maximal globally hyperbolic future developments of generic asymptotically flat initial data are future inextendable to regular Lorentzian manifolds. That's quite a mouthful, but what it basically means is if I give you reasonable initial data, and I just, so I give you a three-dimensional manifold, a positive definite metric on it, and a two-form that represent, a symmetric two-tensor that represents extrinsic curvature. And I evolve it forward by Cauchy development, by solving the Einstein field equations. That gives me a space-time. Is the result I get when I evolve that data forward as far as I can, is it the case that the space-time I get is maximal? Is it is it still a case that that spacetime is still in some sense extendable? If it were, that extension would not be determined by Cauchy evolution. That extension would be that would be a very clear failure of one kind of determinism. That's a very popular way of posing cosmic censorship these days, but it's important to recognize that anything remotely resembling a proof of such a proposition depends on assuming auxiliary conditions, like energy and causality conditions, that themselves are as weakly supported or otherwise problematic as cosmic censorship itself. Once again, there's the problem with the inherent ambiguity of the idea of the inextendability of spacetime. If one chooses a big enough background class of possible spacetimes into which you're going to allow extensions, then essentially every spacetime is extendable. But if you make your class so small that and really sparse, then every spacetime will be inextendable. So you can just either violate or preserve cosmic censorship just by being injudicious, or by cheating, if you like, gerrymandering in your choice of what you take to be acceptable spacetimes. There's a problem with making generic well-defined and physically significant, because remember, we already know for a fact that you can construct solutions that violate any principle of ease you want, that have naked singularities in any sense you want. So the idea isn't to rule out every single naked singularity solution. The idea is you want to say that the ones that naked singularity solutions are rare, they're scarce, they're unstable. The good ones are generic. There's a real problem with making the idea of generic well-defined and physically significant in this context. And as I just say, their counterexamples have been found to essentially every precisely formulated proposal along these lines. So there's a funny dialectic in the field, in the mathematical physics field, in which this kind of problem has dominated for the past 20, 25 years. There's just been the dialectic has been, someone proposes a new formulation of cosmic censorship, gives something like a proof, someone else comes up with a counterexample, then we go back to the drawing board and weaken the formulation of cosmic censorship, give a proof. Someone comes up with a counterexample. We go back to the drawing board, weaken the principle, and that's what's been happening for 25 years. Until we actually now are at the point where the strong formulations are incredibly weak. All they care about doing is ruling out discontinuous extensions. I mean, that's topologically discontinuous extensions. That's crazy. So there are several open and serious conceptual problems here. As I say, there are many different formulations like this. None are equivalent. All capture something subtly very different in conception. Each have their own conceptual virtues and demerits. Which one should one choose? Is it the case that one must be forced to choose exactly one? So I had a really interesting correspondence with John Ehrman about this a few months ago, in which he did this beautiful job of laying out all this stuff. I've been trying to convince him to publish it, but he's even more crotchety than I am. Anyway, there's also the issue that it's just not clear. I am deeply dislike is too strong. I am uncomfortable with 3+1 formulations of general relativity, with initial value formulations of general relativity. It's just not general relativity. General relativity is a theory about four-dimensional objects. Dividing space-time up into 3+1 is deeply non-relativistic. So I find it very hard to believe we're going to learn anything really deep about general relativity by looking at problems that arise because we have assumed from the start that we're only going to deal with spacetimes by looking at 3+1 representations. And why do we focus on indeterminism rather than other forms of pathology? And why expect, again, that one principle will cover all important cases? What justifies the urge to find such a thing in the first place? And why try, again, this is a theme I harp on again and again because I'm so deeply disturbed by this degenerate, unrepentant and degenerate Aristotelian essentialism I find permeating so much of philosophy of physics. I'm a pragmatist at heart. Why try to find the principle of cosmic censorship rather than several different propositions that make precise and capture different aspects of what we roughly and crudely have an idea we want, each relevant in its own context but not applicable universally? I just do not understand this demand for a single definition for what we use a single name for, as though our language came first and the world must conform to our language use. I just really don't understand it. And why look for the cosmic censor? Why look for these principles in the first place? What justifies the urge to find such a thing? What reasons may we have beyond the brute deliverance of entrenched physical theory, which we don't have in this case? We have no evidence about singularities one way or another, except for the Big Bang. Why expect, and that is a naked singularity, by the way, to expect such a proposition may hold? Well, I think that there are three kinds of physical principles that might give reasons for wanting this kind of principle. There are three kinds of physical principles that cosmic censorship might be. It might be one that's required by the physics for any of several reasons. It might be a physical principle that's required on pragmatic grounds for any of several reasons. Or it might be one that's desired for psychological comfort. And I'll tell you what I mean by these. So when I say that a principle is required by the physics, that might mean it conflicts with another prima facie fundamental entrenched principle like conservation of energy. If we could show the naked singularities, in some sense, violated conservation of energy in the appropriate regime, that would be a reason not to want them. If we could show that it blocks theoretical development, say by looking for theories of quantum gravity, that might be a reason to try and block naked singularities. So these would be reasons that would be required by the physics for finding a principle of cosmic censorship. Then there are reasons that are, things that are kind of required on pragmatic grounds. Why do we want cosmic censorship? Well, because if it's not there, then it conflicts with how we like to do physics. Predictability based on initial value problems. I say this is pragmatic because I find it impossible to believe that the universe cares about how we like to do physics. It might be that if we didn't have cosmic censorship, it would be difficult to model some systems for, just for practical reasons, again, based on how it is that we tend to do physics. And these are important reasons. I'm not trying to say that these are insignificant or unimportant. I just think it's important to distinguish them from the physical reasons one might have for demanding a principle like cosmic censorship. And then there are the principles we have that are desired for something like psychological comfort. Well, it conflicts with how we like to do physics. We're comfortable with that. It makes us uncomfortable when we can't do what we're used to doing. There are aesthetic grounds. A lot of physicists find singularities to be really inelegant, ugly. There's the fear of unpredictability. There's this neurotic Cartesian phobia people have of uncertainty. Don't get me started on Descartes. I can give you a long rant about why basically every single problem in Western philosophy, every single problematic aspect of Western philosophy is due to Descartes' completely pathological neurotic phobias. Everything wrong with Western philosophy, I blame on Descartes. Okay, I'll leave it there. So the demand for cosmic censorship, as the ethically evaluative flavor of its very name suggests, and as the connection with determinism shows, I think arises from both pragmatic and psychological grounds. I don't think it arises from physical grounds. At least in our current epistemic state, nothing yet has been shown that satisfies me that it really arises for physical reasons, that the demand for it arises based on physical grounds. So in sum, I claim, we have an example of a sizable subculture in physics working on matters that, one, have no clearly or even unambiguously defined physical parameters to inform investigations. Two, have no empirical evidence to guide or even just constrain them. Three, have the parameters of the debate imposed by and large by the intuitions of a handful of leading researchers. So from sociological, physical, and philosophical vantage points, one may well wonder why so many physicists continue to work on it. In fact, continue to claim, like Penrose did in '69, it's the single most important unsolved problem in mathematical relativity. One may well wonder why so many physicists continue to work on it and what sort of investigation they are engaged in. 52 years of cosmic censorship, and still we do not know what it is or why we should care. I'm giving a talk next week at a conference in honor of Penrose, and he'll be in the audience. I'm going to talk on cosmic censorship and semi-classical gravity. I'm not going to use this slide, but I thought y'all should see it. No one tell Roger about this slide. Although he probably wouldn't be surprised to see me show him the slide, but anyway. This is not to say that mathematical work on the initial value formulation is not interesting and important in and of itself, only that it is not clear to me that the attempt to resolve the problem of cosmic censorship ought to frame and motivate that work. I mean, right now, as I intimated earlier, mathematical physicists, not just one or two, the leading mathematical physicists in relativity in the world right now, and all their followers, which is basically all the mathematical relativists in the world, are obsessed with finding with worrying about the differentiability class of extensions. Can it possibly make a physical difference whether one can extend a space-time manifold in a way that's C1, 1, but not C2 extendable? To take what is these days, in fact, a rather tame example, especially given that no one expects GR to be a final theory anyway. Do we seriously expect such a difference can register in the kinds of emergence of classical space-time geometry that an adequate theory of quantum gravity will admit, except perhaps in absurdly peculiar and isolated cases that people tend to come up with as counterexamples? And I mean, to be fair, some conceptually oriented mathematical physicists have given what I'm saying thought and do have interesting things to say in response. Martin Lesord gave a talk recently at the BHI in which he actually tried to defend the physical and conceptual importance of worrying about the fine details of the differentiability class of possible extensions. I think in the end, I think what he says is really interesting and worth thinking about. I'm not convinced, but it's definitely worth thinking about. So let's think now about singularities and cosmic censorship in semi-classical gravity. So we've already seen the semi-classical Einstein field equation, but it's worth looking at it again. You have classical Einstein tensor on the left-hand side, equal to 8 pi times the expectation value of the stress energy tensor as a quantum operator on the right-hand side. And as I've remarked already many times and hinted at and showed you a few, there are many, many fascinating mathematical, physical, conceptual, philosophical problems that arise from this equation. But sadly, but expeditiously, we must ignore almost all of them here. Right now, for our purposes, the most interesting fact about semi-classical gravity is that it promiscuously, with joyous and libertine, even corybantic abandon, violates every energy condition under the sun. But recall that energy conditions are an essential ingredient, essential assumption used in proving singularity theorems. So if these quantum fields violate every possible energy condition all over the place, and have a really good time doing it, do the singularity theorem still hold? You know, since this is, I know of no case where anyone has shown that an energy condition is necessary for proving a singularity theorem. So strictly speaking, it's still possible that there are singularities and maybe singularity theorems even without the energy conditions. But no one's ever been able to prove a singularity condition without a singularity theorem without an energy condition. And there are a lot of reasons to think that one can't, that energy conditions really are a necessary ingredient in singularity theorems. So do we in fact need to wait for quantum gravity to efface singularities? Because that's what a lot of physicists hope. A lot of physicists hope that a good theory of quantum gravity will get rid of all these problematic singularities. Might it be the case that semi-classical gravity will already do it for us? All these energy conditions are violated. We don't have the singularity theorems. Maybe there aren't singularities in semi-classical gravity. Well, not so fast. Ehrenwald in 2013 proved this really beautiful theorem whose most natural physical interpretation is that, in fact, one should expect singularities quite generically in semi-classical gravity as well. So I'll state the theorem in somewhat imprecise terms. So, suppose there exists a globally hyperbolic spacetime. We all know what that is now. There's a Cauchy surface with a quantum trapped surface T. And what Aaron means by quantum trapped surface, he gives a definition of it. It's a certain kind of null surface that has a semi-classical entropy, so just like the Bekenstein-Hawking entropy, that is decreasing to the future as exactly as one expects to occur generically inside of black holes formed by collapse. Let the semi-classical approximation be valid near this quantum trapped surface. We don't necessarily assume it's valid anywhere else, just near this quantum trapped surface. Then the fine-grained generalized second law requires that space-time is not null geodesically complete. There must be incomplete, inextendable null geodesics. This is fascinating. So here's a case where singularity formation is thermodynamically preferred. If anything like the generalized second law holds in quantum gravity, there really seems no escape. Now you might think that this theorem is actually a counterexample to a claim I made just 3 minutes ago, that it seems like one always needs energy conditions to prove singularity theorems, and there's no energy condition here. Well, actually, this notion of a quantum trapped surface with the semi-classical entropy decreasing to the future, that's morally equivalent to an energy condition. What it effectively guarantees is that you get strong convergence of null geodesics. And that's exactly what energy conditions are used for in singularity theorems, to prove that there's strong convergence of families of geodesics, and that's where you get the incompleteness from. So there's not a classic energy condition here, but there is something that's morally equivalent to an energy condition being assumed here. And there's more. In fact, there's been a whole explosion recently of people proving singularity theorems that are relevant in the context of semi-classical gravity. So Chris Fuster and Eleni Cantu have proved essentially what look like classic singularity theorems, but with weakened energy conditions that they call quantum energy inequalities that we in fact expect to hold for evaporating black holes. Frey-Vogel and collaborators have proved even more singularity theorems with even weaker energy conditions, also applicable to evaporating black hole spacetimes. Ettore Minguzzi proved this, like all of his work, it's just so elegant and beautiful, proved this very elegant and beautiful singularity theorem that have causality conditions that are relaxed enough to accommodate expected pathologies in evaporating black hole spacetimes. But I think it's worthwhile stopping and asking ourselves, is our complete causal curves compatible with quantum gravity in the first place? So we've seen now that semi-classical gravity doesn't seem to help us with cosmic censorship. At least we still have lots of singularity theorems, so we still have to worry about cosmic censorship, especially now that we know that black holes can evaporate, that the event horizon can disappear, and semi-classical gravity tells us there are singularities back there. This looks like we're going to get some naked singularities. And so we might still have, if we really are worried about that kind of thing, we might have to fall back onto our hope that quantum gravity will save us from singularities. But are complete causal curves compatible with quantum gravity in the first place? If you think about a space-time where there's a region where stuff is, curvature is strong enough, energies are high enough, whatever, where quantum gravity effects take over, and the classical representation of space-time geometry breaks down entirely. Now think about any right outside that region where the geometry still is well represented by the classical Lorentzian geometry. We have a causal geodesic headed towards this crazy region. Well, as soon as that geodesic kind of hits the place in space-time where classical geometry description breaks down, not because of singularities, but because quantum gravity effects have taken over, that curve is effectively incomplete and inextendable according to the classical theory. There's still a singularity there according to classical theory. So it's not entirely clear to me what it means to demand that quantum gravity will get rid of singularities when on one very obvious construal, if there is such a thing as quantum gravity and its effects are manifested in the real world, there are going to classically be singularities. So it's of course, the obvious response to that is to say, yeah, but the reason why these curves now are as classically described are incomplete and inextendable is because we have to change our theory. to give an adequate description of what's happening in that region. We can't really even call it a space-time region because presumably the ideas of space and time themselves have broken down in some deep sense. So this is not a singularity in the worrying sense. It's a singularity caused by the fact that we have to change our representations, our theoretical representations. And that might be a perfectly legitimate response. But if that is the response, then it's not so much, then all we have learned is that we can't even formulate the idea of a classical singularity in quantum gravity. But that doesn't tell us that there aren't other kinds of singular pathologies in quantum gravity. It just tells us that we have almost by definition excluded this problematic thing, what we thought was problematic in classical theory. Not that quantum gravity hasn't solved the problem. Quantum gravity has just told us to ignore the problem. Anyway, it seems as though also there are in semi-classical gravity rather straightforward violations of weak cosmic censorship. Where by weak cosmic censorship, I mean no naked singularities. So I think I didn't say this clearly enough before. The terminology is in this field, strong cosmic censorship means statements about mensuality formulation that all the mathematical physicists are working on. Weak cosmic censorship means something like Penrose's original formulation, no naked singularities. All singularities are hidden behind event horizons. So Hod recently showed that based on some not completely unreasonable calculations, approximative of necessity, but seems somewhat reasonable, that Hawking radiation can turn near extremal black hole spacetimes into horizonless naked singularities. But it's unclear whether this effect is stable under asymmetric perturbations, because his calculation depends on the suppression of large angular momentum modes of Hawking radiation, which seemingly implies that the spacetimes he's dealing with are restricted to perfectly spherically symmetric or very close to the spherically symmetric. So it's not clear how stable this kind of calculation is. There are other worries related to cosmic censorship and semi-classical gravity. It turns out that you can get trapped surfaces like the apparent horizon outside event horizons during black hole evaporation. Should we worry about that? Well, many important black hole theorems depend on the assumption that every trapped surface lies behind an event horizon. In fact, almost every single important black hole theorem depends on that assumption. I mean, it's not just an assumption, one can actually prove it. For asymptotically strongly predictive spacetimes satisfying the null energy condition, trapped surfaces will lie behind event horizons. So that fact is then used to prove a whole bunch of other black hole theorems. The no-air theorem, like black holes can't bifurcate, all kinds of really incredibly important theorems. But we lose that now in semi-classical gravity. And again, because trapped surfaces are what is used in most singularity theorems to show that singularities occur. If a trapped surface can migrate outside the event horizon, that seems to suggest that the singularities will appear outside the event horizon as well. There's a subtlety here. All the classic singularity theorems don't allow us to actually locate where the singularity is, with the exception of a theorem that Martin proved recently. All the classic theorems like Penrose, Hawking, and Garroch just tell you that there is somewhere in space-time an incomplete and extendable geodesic. And it's kind of reasonable to assume that it's behind the event horizon and where the trapped surface is, but the theorems don't actually tell you that. Martin's is the only theorem I know of that actually tells you that the singularity, that the incomplete and inextendable geodesic he shows you must exist, actually is behind the event horizon, actually is where the trapped surfaces are. And so if the trapped surfaces can migrate outside the event horizon, maybe the singularities do too. There's an interesting recent argument by Engelhardt and Folkestad that in holographic space-times, by that they mean ones with well-behaved dual CFTs, trapped surfaces must lie inside horizons. And so that this seems to be their way to try and avoid this idea that cosmic censorship in the form of trapped surfaces outside of event horizons can be violated in semi-classical gravity. But I find their assumptions to be really pretty suspect, pretty question-begging. Well, and even though their results are formulated, the way they pose the question and the way they argue and prove it, it's all classical. It still has direct relevance to semi-classical gravity insofar as they do not assume an energy condition. Their definition of evaporating singularity is based on causal structure, and I find it deeply problematic. That's where I think they're really making the question, but that's another long discussion. Still, if they're right, and evaporating black holes are not, then does that mean that evaporating black holes aren't holographic? Because evaporating black holes, if very solid calculations show, if anything is solid, these calculations are solid, show that trapped surfaces migrate outside the event horizon. But if they're right, then what happens to all these sanctimonious holographic proofs of unitarity? If the evaporating black holes aren't even holographic in the first place, then there's not even a worry about unitarity. Maybe that's what they'd say. They'd say, look, we've showed you that you never need to worry about unitarity loss at all because black holes really don't evaporate in any interesting sense. But that by itself would again be a rather remarkable claim to make. And there are other worries about evaporating black holes besides the standard loss of unitarity and page-time problems. As we already discussed, Martin's theorem shows, another one of Martin's theorems shows that evaporating black hole spacetimes are causally discontinuous, which certainly seems to me like a violation of something morally equivalent to some form of cosmic censorship. And I think this really should be seriously disturbing. I mean, I've told you my conjecture that there's just no way any reasonable notion of unitarity can survive in a causally discontinuous spacetime. So then what hangs on cosmic censorship in semi-classical gravity? Well, many theorems in black hole thermodynamics, I really mean semi-classical black hole thermodynamics, require, among other things, that trapped surfaces lie behind the event horizon and that the space-time be strongly asymptotically predictable. But that's exactly what all these theorems about calculations seem to show are false. So will Hawking radiation itself, does that effect depend on a lack of, on something like cosmic censorship being valid? It seems like we might be in danger of losing the physical definitions of temperature and entropy for black holes without if we lose access to all these theorems. This is all, I think, very much up in the air. I already talked about the energy conditions, so in the interest of time, I really want to try and finish today in an hour and a half. I'm going to move on. Okay, I'll conclude the talk by asking whether singularities really necessarily indicate the breakdown of our theory, as everyone and their mother seems to think, or whether there may be a different way of thinking about it. Well, let's ask ourselves if in a space-time where general relativity predicts that there will be a singularity, where exactly does general relativity as a theory break down? You'll hear people say, well, the high energy regime. What exactly does that mean? Well, one might think it means that the stress energy tensor is large, but that is almost a completely meaningless statement. There is no physically significant norm known on the space of symmetric two-index covariantly divergence-free tensors. One way to see that is if you just think about the energy density and observer experience. You give me a stress energy tensor. The energy density an observer experiences depends on the state of motion of the observer. It's the energy density is stress energy tensor contrivected with observer's space-time velocity vector twice. But given that observers can be in all kinds of crazy states of motion with respect to each other, with the very same stress energy tensor, depending on my state of motion, I might measure almost zero energy density, and you might measure some enormous energy density. And the difference is it just has to do with the differences in our states of motion, not anything to do with anything intrinsically physical about the energy, about something like intrinsic mass energy content of the field. So maybe high energy regime means large curvature. Same issue arises. No physically significant norms are known on 4 index tensors that have the symmetry properties of the Riemann tensor. And anyway, it's, as I mentioned earlier, intimated, but didn't explicitly mention, but I will now. There are examples of spacetimes that don't seem very weird, that have singularities in which all scalar curvature invariants vanish. Not just that they're small or don't diverge, they're all identically 0. That happens, for instance, in some colliding plane gravitational wave spacetimes. So that also is why the next one, 3, can't really be the answer. Well, maybe a high energy regime means high gravitational energy. Well, there are no known invariant formulations of gravitational energy. So what one means by like the regime in which general relativity is going to break down because of singularities is not itself well defined. And what's the role of the Einstein field equation? Well, as I've already remarked, as I already explained in an earlier lecture, none. Wall's theorem is an interesting counterexample, possible counterexample. Wall's theorem may in fact depend on the Einstein field equation or the semi-classical Einstein field equation. It's the only singularity theorem I know of that may, but it's a subtle issue. It depends on how one interprets the Bekenstein entropy and the generalized second law. Depending on how one defines the Bekenstein entropy or how one postulates it, if you like, the exact form may, if you want to derive the Bekenstein entropy in certain ways, then the form of the entropy you get, A over 4, that factor 1 over 4, really comes from the Einstein field equation. But there's nothing that stops you from just assuming it or getting it from the first law. In which case, you might think that it's independent of the Einstein field equation. So it's a really subtle issue. I've already told you what I think the actual role of the Einstein field equation is in all of these singularity theorems. So if the singularity theorems don't depend on the Einstein field equation or the semi-classical Einstein field equation, because all these singularity theorems of Fuster and Cantu and Frey-Vogel and Minguzzi and Martin, none of them depend on the Einstein field equation in the very strong sense that I've explained. In what sense can they mark a breakdown of general relativity itself? What actually breaks down, if anything, is the idea of Lorentzian geometry, but not general relativity itself. But it's difficult to make this idea precise, because a singular space-time, after all, is everywhere a well-defined Lorentzian manifold. In every single singular space-time, there is no point at which the metric is not defined, or the curvature tensor is not defined. No such point is part of the manifold. There's no point of the space-time manifold representing our universe at which the Big Bang occurs. You just travel backwards in time. You look backwards in time 14 billion years, and things just kind of stop under various fairly natural ways of measuring. Pressure grows divergently, energy density grows divergently, mass density grows divergently, but they never actually reach infinity. There's no point at which the geometrical structures fail. By definition, a point of a space-time manifold has a Lorentz metric and has a curvature tensor. So it actually is not clear to me at all what it means to say, but which you'll hear all the time. That's why I've been putting in scare quotes throughout this whole talk, that singularities mark a breakdown of space-time geometry. Well, they don't, not in any strict sense at all, anyway. There's an illuminating comparison here. Think about the divergence of kinetic energy terms in finite time in solutions of the Navier-Stokes equations. So Navier-Stokes equations, that's the theory of classic, i.e. non-relativistic, non-quantum, classic viscoelastic thermoconductive fluids. So, pretty good models of real fluids. And the Navier-Stokes equations are pretty complicated equations. They're not quite as bad as the Einstein field equation, but they're pretty complicated. And it is the case, in fact, that under quite seemingly kind of tame generic initial conditions, kinetic energy terms blow up in solutions to the Navier-Stokes equation in finite time. And that really is a breakdown of the theory, I claim, because there really is a point of space and a moment of time at which the kinetic energy terms actually becomes infinite, so to speak, actually becomes ill-defined, because we have a fixed background space-time structure against which it makes sense to ask, where did the kinetic energy blow up? What moment of time did the kinetic energy blow up? That's exactly what you don't have for general relativistic singularities. Of course, general relativity depends on Lorentzian geometry, but the breakdown here, if any, does not come from the Einstein field equation itself, but rather generic features of Lorentzian geometry, such as the Ray-Treduri equation. So the breakdown, if there is one, seems to be something like conditions for the definition of structure required for the formulation of the theory no longer apply. Or perhaps, since the Einstein field equation only gives physical interpretation to conditions on the Ricci tensor, maybe the breakdown is in the possibility of giving physical interpretation to geometrical structures in the conceptual terms of the theory, or when it is in fact Ricci curvature pathology that's involved. Perhaps that marks a breakdown of the theory or theories of matter at issue, but again, maybe not general relativity. But again, keep in mind, I'm repeating this because it's a really important point. Singularities do not even herald the breakdown of the theory in any straightforward sense, because the Lorentzian geometry is always, not even almost by definition, well-defined at every point of the space-time manifold. That various measures of curvature or derivatives of curvature grow without bound along certain truncated curves may bother us psychologically, and it may even be wrong as a prediction. But that does not necessarily mean the theory has broken down in any interesting sense. The theory may just made a bad prediction. Not every bad prediction. When a theory makes a bad prediction, that doesn't necessarily mean the theory has broken down in any interesting sense. And I'll try to make this idea more precise. Now, it may be that this particular bad prediction, if in fact it is one, is fruitfully understood as indicating a regime where the effects of phenomena not treated by general relativity, some quantum or thermodynamically non-equilibrium behavior of some geometrical structure, where the effects of those phenomena become non-negligible compared to the scales at which GR is appropriately applied and predictively adequate, but it may not. Compare Newtonian mechanics applied to bodies with arbitrarily high velocities. Of course, Newtonian mechanics fails, special relativity is the better theory. But I think this is not fruitfully understood as a case in which the theory breaks down, even though some quantities, for instance, linear momentum and kinetic energy, grow without bound. It's just rather that the theory makes bad predictions, and we now have one that does a better job. And so briefly then, what I mean by breakdown here is not just that the theory has made a bad prediction, but that the theory is no longer appropriately applied. It fails to have the conceptual or mathematical resources needed to construct a model of the system at issue that can be checked for predictive accuracy. Now, a good example of that kind of breakdown is turbulence. When classical fluids that are well described by Navier-Stokes approach turbulence, you lose the ability to define quantities like pressure and shear and stress. So you can't even, it's not that Navier-Stokes makes bad predictions about turbulent fluids. You can't even use Navier-Stokes to try to model turbulent fluids because you can't define the quantities Navier-Stokes uses, like pressure and shear and stress. That's not what's happening here. If singularities herald a breakdown of GR, then it means that as a theory, it does not have the conceptual or mathematical resources needed to model, just in the first place, the relevantly quantum or thermodynamically non-equilibrium behavior that X hypothesis manifests in regions where GR predicts strong curvature, but that has nothing to do with singularities or incomplete curves. And as remarked earlier, if classical curvature blow-up heralds the need to use funky quantum structures to model a region of space-time, then ipso facto, any classical curve that enters that region will be incomplete and inextendable according to GR. So what exactly is this promise of singularity resolution by quantum gravity anyway? So given the available data, as admittedly sparse as it is, I think that there are two possible retrodictions that best fit our current theoretical understanding of early state cosmology. One, there is an initial singularity, an entirely generic prediction of classical cosmological models, perturbed FLRWs, the Zecharis models, in both spacetimes, both in spacetimes that have a pre-inflationary phase and spacetimes that don't have inflation at all. That is a generic prediction. Another possible retrodiction is with either a pre-inflationary phase or without inflation, eventually one goes back far enough in dynamical evolution that quantum gravity phenomenology takes over and all bets are off about what space-time structure is possible. But even in the second possibility, it is still the case that, as modeled strictly by the classical theory, all path-directed causal curves still effectively end at finite proper time in exactly the way that true singularities do in wholly classical spacetime models. Thus, from the point of view of analyzing the conceptual structure of the purely classical theory, this still in effect presents us with a situation in which there are singularities visible to the past of non-trivial regions of spacetime in such a way that those singularities visible to the past don't cause any problems with determinism. And they do so in this particular way. So it is the case that there's no way to make sense in the context of classical theory of doing anything like using that quantum region as initial data surface. That just doesn't make sense. But what we can do is say, look, whatever this singularity is, whether it's classic singularity, whether it's just quantum gravity taking over and we can't use our classical theory to model it, we can still just say, look, once stuff has kind of randomly spewed out of it, as it were, in this case, the beginning of the universe as we know it, or something like its FLRW model, then determinism takes over at any finite time thereafter. We can push determinism back as far as we like. And we may cogently conceive of this simply as a perhaps provocative, but still coherent, simply a fixing of initial conditions. Maybe it's not determinate what spewed out of the singularity, but once the stuff did spew out, immediately Einstein field equation takes over and everything just rolls along deterministically. Maybe that's how initial conditions in the universe got fixed. Who knows? So maybe there really are naked singularities and they spew out old socks and TVs playing Nixon's checker speech. And I mean, maybe there really are naked singularities, not just in the past, but maybe there really are some out there in the future, waiting still to happen. In Ehrman's wonderfully evocative and completely horrifying conceit. And if so, we do know that their behavior will not be governed by general relativity. General relativity does not tell us what can come out of a naked singularity. But if we in fact discovered them experimentally, observationally, somehow or other, we gathered observational evidence that led us to say that's a naked singularity. We wouldn't have to freak out. We wouldn't have to necessarily assume determinism ended. We wouldn't have to necessarily think physics is now gone. We could begin to investigate the behavior of these new physical systems as we would any other initially strange physical system, to see whether we can find patterns in it amenable to description by laws in the sense of physics as we know it. Maybe naked singularities, if they exist, really do spew out old socks and TVs playing Nixon's checker speech. But maybe they do it only when stimulated by the absorption of interstellar hydrogen in particular ways. Maybe there are laws. After all, as I have already said, we already know of one case, the Big Bang, in which entrenched physical laws governing stuff near but not at a naked singularity still impose constraints on what the singularity can do. If there were a true Big Bang singularity, the fact that it spewed out stuff that immediately lent itself to accommodation by physics as we know it, perhaps would give us some minimal confidence that other singularities would be manageable in the same way as well. And so deliver us the joy of groovy new physics to investigate with a frisson of concupiscent pleasure. Thank you. God, it's right on time.
Okay, thanks again, Erik. We have time for questions, please. Okay, Marco, please.
I'll be right there. Don't worry. I'm just turning on more lights. Okay.
Hi, Eric. Just a curiosity. Before you were citing this paper from Netta Engerland about the holographic resolution of the cosmic censorship conjecture, let's say, where they prove that trap surface lie behind the horizon in an holographic theory. And then you were saying that there were a few assumptions that they were making that you are not convinced by. So I was just asking if you can tell us which are these assumptions and why you are not convinced by those.
Yeah, sure. To make sure that I don't misrepresent what Netta said, I actually have this written down. So let me. I think I can very quickly find it.
Yes. I think that they showed that if you have an holographic theory, then the errant horizon formation is such that the trap surface lie behind the errant horizon.
So, okay. The assumption that they make that I find possibly question begging. So that you may not be surprised to hear, since I already indicated something like this when I talked about Merle's argument, that all these logarithm groups I know make what I consider to be not completely justified assumptions about the causal well-behavedness of the interior of the space-time. They do that as well, but put that aside, since that's completely generic holography. I'm not going to hold that against them. So put that aside. There's actually another a very important assumption they make that I find question begging, which is they want to claim that classically singularities, loosely speaking, and I'm now using their words, singularities don't evaporate. And then they try to capture this loose but intuitively somewhat clear idea by giving a definition using the tools of causal structure. But since they allow singularities to form, and since general relativity and energy conditions are time reversal invariant, as far as I can tell, they have no reason whatsoever to say that singularities can form, but that they can't evaporate. They seem to me to be just assuming what they want to prove.
Okay, so is this condition about evaporation of singularities? So they just forbid evaporation of singularities, and for you, I mean, since the theory should be time reversal and so on, this cannot be the case because they formed, then they should also disappear somehow.
I'm not saying that this assumption is wrong. This assumption may in fact be an appropriate one to use. But they just don't give a reason for it.
I see. Okay.
They say we're going to assume singularities don't evaporate. Here's our causal characterization of that idea. But they don't give me any argument why I should believe this, when in fact it seems quite straightforward that if singularities can form, then we have to give some reason that they can't evaporate. Maybe it's a thermodynamical reason, but you have to give some reason because the theory allows them to evaporate if they're allowed to form. Now, when I had a conversation with Aaron Wall about this, and I was complaining, it was actually kind of funny. He said, I had a problem with that. I had a problem with that condition too that they assumed, but it wasn't what you're saying. I actually just think that the technical definition is wrong. And so so he told me that. So Aaron has a problem with it too. Aaron has a totally different problem, which is he thinks the technical condition doesn't capture the idea they want. I think that the idea they want perhaps isn't the right idea. So
it's not justified, well justified, let's say.
There may be more than one problem.
Okay, I see. Okay, thank you.
Thanks. Curiel, please.
Yes, Eric, I have several questions, but I have reduced to some essential ones. So I want to come back to the semi-classical description of Einstein's field equations, and then your comment on that, in a way, the violation of the energy condition might come as a free lunch, so to say. I didn't quite get the point how this might arise just by replacing the stress energy tensor by the expectation value from a field theory. So this first, and second, coming just aligning with Marco's question right now, and Wall's theorem, which forbids the singularity to evaporate, how this relates to, I suppose, another theorem or so that you have mentioned, that a fine-grained generalized second law prefers actually the formation of a singularity. So I don't see how these results are compatible with one another, how they relate. So let's
good. Yeah, good. Thank you. Those are questions that I think will hopefully help clarify some things. So the issue about violation of energy conservation, there's no theorem or result I can point to. It's actually a rather straightforward calculational fact. You write down that. So I guess in a sense it is a theorem, but it's just that when for a very wide class of Lagrangians, for quantum fields, it's very straightforward calculation to show that that insofar as one can make sense of defining the stress energy tensor operator and calculating its expectation value, which are themselves non-trivial, that it's very easy to show that just generically they will often be negative. It's just there's not. I can't give you a good physical reason or explanation for that. It's just a fact about quantum field theory. I mean, it's not even restricted to quantum field theory in curved space-time. This happens in ordinary quantum field theory in Minkowski space-time. The Casimir effect. The reason why there's a Casimir force between two conducting plates in vacuum is because there's an effective negative energy density between the plates that pulls them together. So this is a fact about, this is just a generic fact about quantum field theories, not even in curved space-time. They generically have negative, they generically manifest negative energies. What's miraculous is that they always seem to do so in a controlled fashion. That whenever there's a lot of negative energy over here, it seems like that there are some results that strongly suggest that whenever you have a lot of negative energy over here, it has to be compensated for by a lot of positive energy over there. So it seems to be the case that quantum theories always kind of, on average, give you positive energy. But that's consistent with, and in fact, seems necessary to have quantum field theories always having that negative energy somewhere. It's a really interesting problem. God, I sound like a broken record. Everything is an interesting problem. Well, it is, damn it. Your second question. Aaron's theorem, Wall's theorem, says that, doesn't say that I don't know of any theorem that says singularities can't evaporate. Aaron's theorem says if you assume the validity of the GSL, then there must be singularities. Engelhardt and her collaborator, whose name I cannot remember, Folkestone, assume that singularities can't evaporate. But Aaron's theorem is consistent with the evaporation of singularities. Aaron's theorem just says singularities will form. Aaron's theorem doesn't say once a singularity has formed, it exists forever. Does that help?
Yes. I'll thinking about it, and then maybe the others can go ahead.
Okay, thanks. Yichen?
Oh,
Sorry
good.
for my pronunciation.
Good, Yichen. I was hoping you would speak up. You already told me that you were going to disagree with me.
Actually, I mean, it's really a wonderful talk, and I mean, a lot of materials I need to digest before I have really critical or supportive idea. But the thing I'm wondering now is I always take singularity theorem as an independent criteria from GR, right? So the way you use or we think of singularity theorem is that it helps us to check or to see the way we describe the space-time or the universe is problematic or not, right? So we use singularity with the interpretation from GR to check the model we build for black holes or for the space-time is right or not, right? This is my basic view. Okay. So now we consider exact model, say for the Curiel solution, right? So we did have some physical version of energy condition, aside from geometrical version of energy condition, right? So we know it satisfies the conditions, interpreted conditions in singularity theorems, and we know there's some region. Once you into that, or you at that point, you cannot use general relativity to describe the behavior or the space-time there. So in that sense,
wait a minute. Once you enter what region, you can't use GR?
Yes, exactly. Yes.
No,
I mean,
no,
you don't.
Which region? You
well,
said once you enter the region, you can't use GR. What is the region you're referring to? I missed that.
Okay, so basically, I think it's the region. I mean, inside the trap surface.
So and you're talking about Kerr, right?
Yeah.
So the singularity forms behind the Cauchy horizon. So is the issue that you're worried about evolution beyond the Cauchy horizon?
Yeah, kind of. Yeah, maybe. Yeah. Thanks for pointing it out. Yeah.
And also this is another subtle point. None of the classic singularity theorems actually apply to Kerr. Kerr doesn't satisfy the conditions of any of the classic singularity theorems, because every single classic singularity theorem assumes a causality condition that Kerr violates.
Well,
the fact that we know there's in some sense of no, the fact that we know there's a singularity in Kerr is because we calculated it from the metric. It's not as a result.
That's right.
But
not as a
result of any singularity theorem.
Okay, good. I mean, now that's drop the Curiel case. I mean, I need to check that whether that apply or not. So let's just think about this the most easiest. So the stretch black hole, we need to check whether this idealized model works or not, or whether, I mean, under such and such condition will it form physically. I mean, physically, but by saying physically, we use general relativity, right? So it is the role of singularity theorems for us to check whether this kind of model as meaningful or meaningless, right? Mm-hmm. I mean, depends on your understanding of meaning. Mm-hmm. And I mean, that's just my basic view of how you think of singularity theory. So in that sense, I don't think physicists or their mothers use this breakdown as the Jones is the sense you use, right? Mm-hmm. They definitely, what they are doing, they still use general relativity, right? You use it to improve it. It's just not the sense that they want to drop it. Mm-hmm. In as much as the same way we think of Determinism theory, right? Mm-hmm. So I basically agree your conclusions, but I mean, I need to check the details in your argument. Yeah, so this is just a comment. Okay. And the question is, really I want to ask a question about the cosmic censorship conjecture. So as you mentioned, for the horizon of a Curiel solution, you basically calculate the control variant tensor matrix G11 to get the horizon, right? So if the acceleration satisfied, I mean, it's not an extremal black hole, you know there are two horizons. But if the acceleration is larger or equal to larger than the mass square, then there's no horizon, right? So this is the exact model we know about naked singularity or horizons. And my question is, historically speaking, because you know a lot about cosmic censorship, is there any relationship between you find this exact solution and the motivation for like promoting propagating the cosmic censorship conjecture? It's a historical question.
Yeah, I don't think so, because and I probably wouldn't have felt so confident in asserting that just like 2 or 3 months ago. But recently, almost like completely because of different reasons, Klaus Landsman and I got really interested in the question of exactly when the classic definition of an event horizon was first formulated and by whom. And so we both of us kind of just got a bee in our bonnet, and we went back and started rereading all the classic papers, and we had a lot of correspondence back and forth. And so I actually have a lot of that history now very fresh and vivid in my mind. So you caught me at a good time. No, the maximal analytic extension of Kerr that shows that beyond the Cauchy horizon you have these closed time-like curves, and you have the ring singularity, and you have the tunnel into into a new kind of anti-universe and all the crazy stuff. Carter developed that sometime around 1970. So Penrose had already formulated the cosmic censorship hypothesis in 1969. Penrose is very explicit in his 1969 paper. He's just worried about just ordinary gravitational collapse, of a real astrophysical gravitational collapse, because there was a real worry back then that, again, as so often the case, Penrose was the first to articulate that they had no reason to think, except that they really wanted it to be the case, that event horizons were stable. As far as they knew, as far as their calculations showed, their model building showed, their principles showed, their arguments showed, nothing precluded the following from happening. You have a collapse, you have an event horizon forming, and it just hangs out for a while. And then someone strolls by and just throws a tiny bit of mass into the black hole. And the event horizon just disappears. There was nothing that ruled that out. So this is known as the black hole equilibrium problem. So that's what Carter called it. And there's still not a proof of it. There are a lot of there are proofs of various kind of very mild, weak, very restricted claims along those lines. There are very, very compelling heuristic arguments that really strongly suggest it's true, but there is no completely general proof that event horizons are stable. So it was really that kind of thing that Penrose was worried about when he proposed cosmic censorship.
Let's see. Yeah, that's helpful. Thanks a lot.
Thanks. Other questions? Enrico, please.
Hi, Erik. Thanks a lot. That was illuminating. I have a small doubt. I mean, I have many questions, of course, as you may imagine, but I just wanted a bit of a clarification on something which is maybe connected to what Marco and what Curiel were asking, because I'm too puzzled by the result of Engelhardt and I can't remember the quote or. Huh?
Oh, no, not Fulkerson, it's Fulkerstadt.
Fulkerstadt, yeah. So Faulkner is another one. Yeah, I was really puzzled. I was especially puzzled by your gloss when you said that this result seems to imply that there cannot be any holographic dictionary for evaporating black holes. And I wondered if you could maybe say a bit more about that. Why do you think that result implies that you cannot holographically represent evaporating black holes?
Yes, so my claim wasn't so precise that you can't build a dictionary. It's not clear to me if my claim is correct. I made the claim very vague, and I did that purposefully because I'm not sure exactly what the right claim will be, because they aren't very precise about it. But what their theorem shows, mathematically, I think the theorem it is a theorem. It is a mathematical result. The problem that Aaron has with it, the problem that I have with it, are the assumptions. Whether the assumptions are reasonable or really capture what they want to capture. But let's assume for the minute that actually that it is all good, and their assumptions are well motivated. They can give good motivations for them. That the assumptions really do capture what the physical picture of what they're trying to capture, and we get this result. Well, the result is that in holographic spacetimes, trapped surfaces always lie behind the event horizon. But it's a completely generic feature of, I think, of compelling, well-supported calculations in semi-classical gravity that when black holes evaporate, the apparent horizon eventually migrates outside the event horizon. But the apparent horizon is a trapped surface. So the issue is that if they're right, then, and I guess I should remark that when I say that these calculations that show this are strong and compelling, and of course I've been telling you nonstop for 5 days, don't trust anything in semi-classical gravity. I mean, I haven't really been telling you that. I've been telling you to be more skeptical, to only be more skeptical, not don't trust it at all. But these calculations really are, I think, if anything is strong and compelling in semi-classical gravity, these calculations are that strong. In fact, Netta herself, with Rafael Busso, gave, I think, the strongest argument that apparent horizons migrate outside the event horizon. It is in a paper I quoted in the slides, so you can find it in the bibliography of the slides. So I think there are really good reasons to think that if semi-classical gravity is a good approximation, if it is a good framework, then black holes really do evaporate, then yeah, the apparent horizon eventually migrates outside the event horizon. But that violates the conclusion of their theorem. So by modus tollens, that space-time can't be a holographic space-time.
Sorry, just to be sure. So, but didn't you say that one of their assumptions was that they're not dealing with evaporating singularities?
Yeah, there's a difference between an evaporating black hole and an
Okay.
evaporating singularity.
Okay.
The evaporating black hole means the event horizon disappears.
Mm-hmm.
The evaporating singularity means the singularity disappears. Those are both logically and physically and conceptually independent of each other. So they're assuming that singularities don't evaporate.
Mm-hmm.
Their conclusion is apparent horizons don't migrate outside the event horizon.
Okay.
Can you repeat that last sentence?
So they assume that singularities don't evaporate, and they conclude from this that apparent horizons don't migrate outside, that apparent horizons never appear outside the event horizon. Trapped surfaces never appear outside the event horizon.
Now it makes much more sense. So they then they don't have to assume that the apparent horizon goes before, so to say, the event horizon, so it doesn't leak out of the.
Is it that they're not assuming that, they're trying to they prove that the apparent horizon is always behind the event horizon, given these holographic conditions.
Okay, we have a time for other questions, clarification or others.
If I may.
Yeah.
So one of the interesting things that you mentioned, I think, is that in Wall's theorem, the generalized second law is assumed, and the generalized second law relies it does rely on invoking the Einstein field equations. And so my question is, how does that actually come about? So how does this thermodynamic sense leak into the Einstein field equations? Is it by some kind of entropy that enters the equation of state, and so you have it in the stress energy tensor, or how does it leak in?
So what's happening is that, so we think that in general relativity, the Bekenstein-Hawking entropy of a black hole is the area of the black hole divided by 4, ignoring all the the constants. It turns out that in other very closely related theories of gravity, FR gravity, various kinds of more generalized Lovelock-Langsos theories of gravity, you can do very similar calculations. You can do the analogous calculations, and you get that the analog of the Bekenstein-Hawking entropy is proportional to the area, but it has a different coefficient. It's not 1/4. And in fact, there's a completely general result that will allow you to calculate very easily exactly what the form of the analog of the Beck-Einstein-Hawking entropy will be for a black hole in a very wide family of alternative gravity theories by Bob Wald in a paper from 1981, maybe something like that. The paper is called "Black Hole Entropy is the Noether Charge." And he actually shows you how to derive, given the Lagrangian for the gravitational theory, he derives what the form of the Beck-Einstein-Hawking entropy must be. And the Lagrangian, the Einstein-Hilbert action, the Einstein-Hilbert Lagrangian gives you the 1/4 coefficient. So that's the reason why the exact form of the GSL that Aaron uses and the standard form of the GSL, A/4 plus other entropy never decreases, that actually seems to depend, that does depend, it seems, on the Einstein field equation, on the exact form of the coupling between stress energy content and space-time curvature in a way that almost no other theorem in this part of general relativity does. So that, I mean, to me, that's a really tantalizing fact, that the only time you ever actually need to invoke the Einstein field equation in anger is for the generalized second law. So that does seem to suggest maybe, you know, if you squint your eyes hard enough and don't think too carefully and are really juiced up on some good adrenaline, that maybe, you know, Jacobson and Padmanabhan's programs are really onto something. There is something already very deeply thermodynamical about classical gravity.